Hello ladies and gentlemen, today we're going to be looking at flow rates and in particular how flow rates behave at certain temperatures and pressures. So the problem we have says if CO2 flows at 0.0611 grams per second at standard temperature and pressure, calculate its molar flow rate in moles per hour and its volumetric flow rate in milliliters per hour. Okay, so we have some important piece of information here. We have the mass flow rate of CO2. And we're also told that it's at standard temperature and pressure. So what is the significance of this? STP is just the standard temperature, which is 273 Kelvin, and the standard pressure, which is 1 atm. And we'll see where that comes in just a second. All right, so let's write what we have. 0.0611 grams of CO2 is flowing per second. And we want to get the molar flow rate. Okay, so right away I see we can change the seconds to hours with the relationship of 3,600 seconds per 1 hour. Alright, and now we have grams of CO2 per hour, but we want moles. So we need a relationship there, 44 grams of CO2 per 1 mole of CO2. Okay, and then we have our final units here. We have moles and hours, which they said in the problem that's what we wanted. So if we do the calculations at this point, we'll get the right answer, and rounding that to 3 significant figures, 5.00 moles of CO2 per hour. Okay, now what about the second part? Now we want the volumetric flow rate in milliliters per hour. Okay, so this is where the standard temperature and pressure comes in handy. So you may be thinking, let's use PV equals nRT. And we have the moles value, we have the temperature, we have the pressure, we have the R constant, and we could just solve for the volume and get the volumetric flow rate. But what if I told you there is an easier way? So at STP, we know the specific molar volume. Or at least if you don't, you will in just a second. So the way we write that is V with a hat and the subscript S, and that is in the unit of volume per moles. And one of the most common values for that is 22.4 liters per mole. And this is a very useful conversion factor. And how is it useful? So if we write the molar flow rate, so 5 moles of CO2 per hour, we can now do the conversion to get the volume. So for 1 mole of CO2, or 1 mole of any gas at standard temperature and pressure, there are 22.4 liters. And then we want milliliters, so for every liter there's 1,000 milliliters. And doing that calculation, we have the units of milliliters, hour, that's what we wanted. So we get our flow rate as 112,000 milliliters of CO2 per hour. Alright, here we have a second example, and it says that the volumetric flow rate of air at 0 degrees Celsius and 760 millimeters Hg is 3 meters cubed per hour, and we want to know what the mass flow rate of this air is in kilograms per hour. So we have a few useful pieces of information. We have that the temperature is 0 degrees Celsius and the pressure is 760 millimeters of Hg. And what is this equivalent to? Well, if you don't see it yet, when we convert 0 degrees Celsius to Kelvin, we get 273 Kelvin, and this is the same as 1 atm, and this is standard temperature and pressure. And this is useful because we will again be using that specific molar volume value, which was 22.4 liters per mole. Or another way we can write that is 22.4 meters cubed per kilomole. And for this problem, I think it'll be more useful to use this conversion factor because we have the meters cubed. Alright, so eventually we want to get to the mass flow rate in kilograms per hour. And when going from volume to mass, we need to break this air down into its components. So we know that it's 79% nitrogen and 21% oxygen. But one important detail when breaking down air is this percentage is by volume. So whenever we break up air into its components, we must break it down from the volume. We can't do it at the mass stage because this would not be correct. So thankfully we have the flow rate of air in the volumetric flow rate. So 3 meters cubed of air. We can now break that down into its components, which are 2.37 meters cubed of N2 per hour. And the other component, the remaining amount, is oxygen, 0.63 meters cubed of O2 per hour. And to get the mass flow rate of air, we need to get the mass flow rate of each of these components separately and then add them. So first we need to change the volume meters cubed to moles, and that conversion factor is 22.4 meters cubed for every 1 kilomole. And we have the same conversion factor here. Alright, so the reason we had to split this air up is this step right here. Alright, so the molar mass of N2 is 28 kilograms per 1 kilomole, and for oxygen it's 32 kilograms of O2 per 1 kilomole. So I put this in a different color because this is the point of difference. This is where they are separate from each other. So what do we get? We get 2.9625 and we get 0.9. And the units of each of these is kilogram per hour, kilogram per hour. Alright, but we wanted the total mass flow rate of air. So we have to add the two components here, and if we round to our three significant figures, we will get that the mass flow rate of air is 3.86 kilograms of air per hour. Alright, I hope you found this helpful, and if so, please check out the other videos. As always, thanks for watching.